Okay. Yeah, should be working. Yeah, it's recording. Okay. All right. Thank you. So let's see what we're gonna do. Okay. Try to connect. Okay. Let me do it while I can. Okay, welcome. So let's see. Everybody got a syllabus? Okay, so this is Math 347, Bayesian statistics, and it's offered at Vassar. So I will go through. So in the introduction slides, I posted online already. If you have looked at it, you will know we're gonna go through course orientation first, especially about the online part and also the collaboration that's going on. And then we're gonna just have the regular introduction to the field. And then we're gonna, I think this is gonna take today and part of Wednesday or entire Wednesday, and then we'll, yeah, there will be like few like later lectures later. Okay, so let me get this right. Okay, so everybody can hear us, right? Okay. Okay.
Yeah.
All right. So okay. So I'm using this. Okay. Anyway, I'm just gonna do it. Okay, so what we're gonna do today is I will talk about the course orientation, and I think we can get to the interpretation of probability and Bayes rule, and part of Bayesian inference. Okay, so for the introduction lecture itself, I think it's gonna go today and Wednesday, and the last part will be of some review of probability, and all of the slides are here. I might make updates, but I will keep everybody posted about all of this. Okay, so course orientation, there are two parts about this. First, I want to talk about the course itself, like the topics that we're going to cover and some logistics, and then later to this online collaboration thing, okay? Okay, so office is 403. We have a stats intern, Bayan. He's a senior math major, and he took this class with me last year, and he's really good. So we just don't know yet his hours, but he will be the graders for this class, as well as, so, you know, like in our department, we have the stats intern position where they're gonna hold office hours, and he's a designated stats intern, okay, for this semester stats courses. So he, yeah, we'll get more information once we know about his office hour schedules, and I will post that on Moodle as well. So lectures is gonna be Mondays and Wednesdays in this room, 1:30 to 2:45. So it's slightly different from the regular math class that we have. We meet twice a week here. Yes, okay. And labs, so this class we use R very extensively, and I know some of you have experience, some of you might not, and I will try to keep everybody on the same pace as much as we can. And I will talk about this aspect later, but because of this online collaboration, I'm actually thinking about bringing certain things, like, because now I can make videos, and I will try to, like, maybe installing R, downloading R, do this little toy example. I might try to make videos for R, as well as some of the review material. Okay, so later you'll see that because we want to record everything, I will have to write on this iPad. So I think it gives me less freedom than if I can write on the board, and also this is a little bit like smaller. But so one way I'm thinking about getting around this will be making videos of some review of linear algebra, for example, like a lot of matrices are over there. So I will like experiment along the way as well, but feel free to give feedback as much as you can. And I will talk more about that aspect later, but just so you know, some of the lectures will be used as labs, and for the online, for the remote students, we're gonna, yeah, we will still be able to, so by the way, all of the app is called Zoom, Z-O-O-M. So we're gonna zoom them in or like zoom them out. But anyway, so we will be able to do that for the labs portion as well. And also, yeah, so then for the office hours, I have regular office 3 hours each week, Monday 3 to 4, pretty much right after this class, and Tuesday 1 hour in the morning and 1 hour in the afternoon or by appointment. We're gonna have separate online office hours for the remote students. So for all you guys, we're gonna coordinate once you know better about the schedules that you have. And Bayan's, the interns and graders office hours, I think he will only hold like face-to-face office hours. And we will announce that later, okay? Okay, okay, so for everybody here, the prerequisite is 220 multivariable calculus, 221 linear algebra, and 241 probability. okay? And equivalent to, so for the remote students, going to be like the equivalent courses at your own institutions. And I want to say for everybody here, did everybody take 241? Okay. Anybody took 209 instead? Okay. You took both? Okay. You only took 209? Yeah, so that's 209, and you did that as well? Okay, and okay. Yeah, so couple, I think 4 or 5 of you, it's no problem. And, but you might, I guess, you might have a slightly weaker background in terms of probability. So make sure that you try to catch up along the way. And we're gonna provide, like say, oh, somebody just, oh, hi. So that's, did anybody pop up? Okay, I can see something else over here. Anyway, so what I was saying. Okay, so for 209, I think it's okay. And for the probability review, like I'm gonna provide part of it for the introduction lecture, probably mostly on Wednesday, and then I would try to provide some other like reading materials. I mean, like handouts or like maybe videos. I don't know yet, but I think for the students who had only 209, just be a little bit more engaged in terms of catching up the material, because it's just like last year when I taught it, we had 11 students and 1 student had only 209. I think that student struggled a little bit more, but it's hard to tell whether it's because of 209, right? Yeah. So, but still, I think my guess is 209 might be a little bit weak in that. But just a few of you, and keep talking to me if you have any questions. Okay, so that's that, and let me. So the textbook we're using is, yeah, so this is first course in Bayesian statistical methods by Pierre Hoff, okay? And I think it's 2010, that's the only edition. And we used this book last year. I think it's good and bad, again, for any textbook. And there are certain things, okay, so we're gonna follow this books mostly, but there will be some additional material that I'm going to add in along the way. I will talk more about that later. Some of the additional topic will be just pretty like different topics that people might be interested in. So that we're probably going to borrow heavily from other books. But another source of additional material for this, I think, is some students from last year complain about the sample code that they provide. They think it's not useful. I don't know if it's wrong or anything, yeah, but they complain a little bit. So I think for this time, if we're gonna draw from any of the sample code that they have, I would definitely double check and then make sure that I post the version that I think at least works well on Moodle before we're gonna go into it. Okay, so these are the most, I think that's the most complaints that people have about this book. But other than that, I think it's a great book with like all of the sections listed very well. And I think also like the flow, like the order of the topics that they have, we're gonna follow that. Not in the right, like not in the exact order, but we'll be very closely. So definitely get a book and start reading again. And okay, so the software, so we're gonna use R for the lab sum project, and R. And in particular, you should download R, install it, as well as RStudio. Okay, so RStudio is a convenient interface. So last year, or like for many other stats courses on Vassar, we just use the Vassar server, like the RStudio.Vassar. And the thing is, sometimes that is down, and if a lot of people like this computation, the computation from this class will be a little bit more than the regular, I think. So I will strongly recommend everybody download R and install an RStudio as well, and it's going to be very useful for later as well. Because for RStudio, like the Vassar server one, you can only log in once you're connected to Wi-Fi here. There's so many restrictions in addition to the slowness of that. So definitely make sure that you download it. And so just so you know, so part of it, if we're gonna do some demonstrations, I'm gonna like call in using my laptop, and then I'm gonna take control of the Zoom. Then everybody can see my screen with the R demonstration. Okay, so that should be working. Like I tested out, I think that's fine. And so that's gonna be like some in-class demonstrations with R, as well as for the labs we're gonna do it. Okay, all right. And the webpage, I know, I guess remote students still don't have access to Moodle. We're still working on it, sorry, but for now, until you have access, I would definitely make sure that I will send everything to you all, like through email. and I can check who can use or who can access Vassar's Moodle. So once I know that, I think I will be fine. So Vassar's Moodle will be the main thing that we're gonna use, and you should check the site for homework, meetings, announcements, and also, in particular, I use Google Docs. I made the rights to see to anyone who has the link. So I think everybody will be able to check it. And I think some of you already filled out the survey. That's also by Google Docs, like Google Forms. And I think some remote students have done that already. So I would imagine that's fine. That's working fine for everyone. Okay, so yeah, updates over there, and any reminders of homework, etc., I will definitely send out email and announce in class. So I wouldn't, yeah, so you all have access, I think. All right, so, okay, so for the course topics, I want to give an overview of the entire class at the beginning so we know what to expect. So overall, so in my syllabus, so for everyone who has a copy of the syllabus here, you look at it on the first page. Yeah. Oh, by the way, I updated, so it's a little bit different from the one that you have on the Moodle if you printed out before. But what is on the Moodle is the most updated one. Okay. So, everybody has a copy. So if you look at the first page, I try to put down the topics, like the outline of what we try to do, and it's a rough breakdown of the 3 parts, but I still want to talk about it, especially at the beginning, to give you a sense of. Say, if in the end I want to do a project to analyze the problem using Bayesian methods, what I should know, okay? And the things, so, okay, let me maybe show all of them together, and then, yeah, it's just too much, I feel, like if I, okay, but anyway, okay, so there are 3 different parts that if we try to divide, like the material for this class, so think about, somebody just left the meeting. Okay, inference, computation, and application. So inference, mostly going to happen at the beginning for the first few chapters. That's talking about like how to use Bayes theorem, what Bayes theorem is, and you will know that we're going to start talking about prior distribution, posterior distribution. So we're going to cover that at the beginning in different contexts, and also how to make inference. Say, if I want to do prediction in Bayesian statistic or Bayesian methods, we call it predictive distribution, etc., etc. And HPD interval is just an analogy to the confidence interval that people have for the frequentist method. Okay, so I just list the topics here, and it pretty much covers the textbook chapter 1, 2, 3, and 5. Okay, so that's inference. And another big area, or I think a big component of Bayesian analysis, is the computation part. Okay, so we need to know how to do it, why it works, and then also, I mean, how to do it not only just on paper, but also how to do it in R. So that would be, I put it as a second part of this course. So we're going to start with Monte Carlo approximation, that's chapter 4. And then we're going to move to Markov chain Monte Carlo, we call it MCMC. And that's pretty much, if you hear about, I think if you hear people talking about Bayesian analysis, like they all talk about MCMC, but it's just a general name for this general method, but there are so many sub methods nested in it. So the one that we're going to talk, the first one we're going to talk about is Gibbs sampler, and then we're also going to talk about metropolis listing. So don't worry about the jargons. I just want to give you a sense of what is embedded for each of the part. And then we're also going to learn about diagnostics, because when you run a simulation, or if you run, in this case, Markov chain Monte Carlo, we want to know if this simulation can converge to the analytical results that we might be able to get. Okay, so pretty much you can imagine like inference. So Bayes theorem, if we go back to the first part, the Bayes theorem and prior, et cetera, they're not that hard to do, especially with the ones that you have nice properties. You can just see the results directly. But for a lot of complicated applications, you will have to use computation to approximate it. So that's what we need to know about the computation part. And I said in that there are multiple aspects or multiple ways of doing it. And then in the end, we should do diagnostics, because we don't know how good the approximation is. And then there are certain ways that we can check, like empirically, to see if that works. Okay, so, and also something new from last year, I think, comparing to last year, is I want to use more R packages this time. And it's mostly called Winbucks for Windows machine, and JAX. So JAX is just another Gibbs sampler. So JAX, that's for the Mac machine, I think, for our packages where, so, okay, so maybe let me get it started a little bit here. So for the computation part, so pretty much, say for inference, for example, we're going to talk about conjugate prior, where there are a lot of like nice results over there that you probably don't even need to do fancy computation. You can get the analytical results directly. But for those for situations where you cannot, say non-conjugate prior, for computation, you can do Gibbs sampler, you can do a metropolis hastings, and sometimes it can get very complicated. Depends on what kind of prior distribution that you want to give for the parameter. So we're going to try to use, in order to understand like some of the modeling aspects of it, we won't be able to code it up by ourselves because it's going to be too complicated. We're going to utilize our packages such as Winbugs and JAX to do that for you. So, I mean, I will announce that later when we get to that point, but I do want to point it out right now. For the computation, we have two parts of it, okay? One is we actually going to code it up, the program. The ones that are nicely done, and we can actually do it. That's going to be practice for coding. Exercise for coding, and then also just understanding all of the algorithm better. But there will be like some other more advanced methods that we won't be able to code it up, but those methods will be more applied, and you can use it in many other areas. So for those cases, we're going to utilize those R packages. So the goal over there, so the syntax will be easy. They have a lot of stuff for you already. It's probably just a few lines that you can do something like fancy. But the point over there is how you're going to understand, say, why it works and how well it works, things like that. So it will be more about like choosing like, oh, now because I don't care about like the coding itself, the package is going to do that for me. I can try different priors. I can get very complicated. But then the question is, oh, how am I going to choose prior? How am I going to like whether prior A is working better than prior B, et cetera, et cetera. And if I have multiple different models, how I'm going to choose between them. So those will be done much easily if we're going to use our packages like Winbugs and JAX. And so we're going to try to incorporate that as well. And I think that can carry like for you all. I think that can keep you going further like after this course or after graduation if you want to use more methods over there. Because right now, they're just the packages, but there's so many different models that you can do with these packages. So if you say go to work for a company and they want to implement some Bayesian methods, most likely you're going to use these packages, comparing like instead of doing it by yourself. They're going to be time consuming, et cetera, et cetera. So I think understanding how packages works and how to use those packages, how to make decisions based on those packages is still very useful. Okay. Okay. So for the computation part, it's going to be chapter 4, 6, and 10. Pretty much. And the last part is applications. Some of them are covered in the textbook, some of them are not. And okay, so Bayesian, okay, so the hierarchical modeling and linear regression and latent class modeling, I think they're covered in this book. And the last two topics I wrote down, Bayesian time series modeling and Bayesian cont'd modeling, is just based on my experience from last year. So this week, later when we talk about the project, we can talk about it again. But here I want to just highlight, based on my 1 year experience, I think on this campus, for people who like taking this class, if they're single major just want to know about like Bayesian stats, that's great. But if it's double major, it's most likely double majors with econ or double major with cognitive science. Okay, so that's just my observation so far. So I try to, if we have the time at the end, I want to introduce some of the topics or some of the methods in these two areas. So mostly for the econ guys, I think it's mostly about time series modeling. If you have time series data, what kind of Bayesian methods you have over there, like exchange rate, interest rate, et cetera, if you want to do that. Cont'd modeling, to be honest, I don't know anything about it at the moment, but I started reading things about it, so I think later I will know better. And then depends on like the entire class, including Vassar students as well as remote students, depends on your interests. We can see if we want to tweak here and there for the topics itself. But I wrote them down over here because I think that's what most people are going to be interested in doing, say, not only just for their project, but also for later if they want to use the material from this course for future work. I identified these two big areas for now, but we can keep updating based on how we feel. And then you can give me feedback as well as like what kind of method or what kind of things, analysis that you want to do. And then if we can see if it's going to be like a few of you, then it will be much easier if I spend one lecture covering the basics instead of you all do separate work for your project and in the end find out that you were doing the same thing for the first 50%. Okay, like the literature review or just get the things ready. So that's just what I have in mind at the moment. So for the applications, yeah, we call it applications, but it's still very like embedded with the inference and computation from before. Okay, so actually, I guess I have one more. Yeah, I wrote it down, not necessarily this order. Topics actually depend on each other from all of the different parts. Okay, so say like once we get to Bayesian, so just for example, if later when we talk about Bayesian hierarchical modeling, I think we might actually talk about it together with Gibbs Sampler, because they just like work together very well, and then one explains the definitions and all of the stuff from the other. So I think that would be easier done in that way. But I would like definitely like announce and then keep you informed from the beginning to see like, okay, this is about computation, but this computation is specifically for this kind of model. So pay attention, things like that. Okay, any questions? Any questions from you guys?
Nope.
Hey. Okay, so
wait, right when we have a break.
So let me just explain a little bit about this experiment. Especially, I think like the remote students might know a little bit more, but us, like the Vassar kids here, probably don't know much about it. So Vassar is one of the 11 schools of this liberal arts consortium for online learning. I think it was established maybe 2011 or 12, around the times when MOOCs got really popular, the massive online and open courses. Yeah, like Coursera, Udacity, et cetera, So a lot of things start to move online. But most of the, I think most of the liberal arts colleges, because we have a different view of thinking about like student-faculty relationship, et cetera. So I think a group of schools, I think it started as 9 and then this year got 11 schools. They wanted to, I guess, experiment and explore like different ways. Not exactly just adopt like MOOCs, just like Coursera, you have more than 1,000 students taking one course and you have like numerous TAs for that. So I think that's how this LACO, Liberal Arts Consortium for Online Learning Consortium started up. And only actually recently, actually I think, let me see, give me a second. Yeah, so what we're doing now is part of the 2-year pilot study. So the goal, so what we're doing now is called the Upper Level Math and Stats Project. The goal is to enrich the upper level math and stats offering across these 11 schools. So pretty much we noticed that most of us noticed that the mathematics courses and the statistics courses as well, that because each school is small, and then the expertise, say like, this is an elective course, right? Like, and then I do Bayesian statistics, so I'll be willing to offer like a top class on this. But say some people here, like some master students might be interested in, I don't know, spatial statistics, but neither me or Professor An is doing that as our research. So even if we okay, I gotta, okay, never mind. Sorry, I guess, oh, you can see here. Okay, yes, so it's okay now, I guess. What I was saying. Okay, right, so if we try to do like a spatial class and then neither of us is expert in it, it's gonna, and plus with the staffing like restriction that we won't be able to offer that many higher level classes. So this is part of the effort to see if this kind of sharing mode can work across the schools, and to see if, say, in the future, if each year, like a few of the stats faculty members across the schools are willing to offer like a topic course like this and offer it through like online and then across the consortium to see if other students can take advantage of it. Okay, so this is part of the pilot study, and it's a 2-year period. So in the spring, Steve Miller from Williams College, he taught a course on, he's a math professor and he taught problem solving. And this semester it's me teaching Bayesian stats, as well as Steven Garcia from Pomona, he's teaching real analysis. Okay, so so we are all experimenting, I think, different technologies. So I know like for the math courses, they're not using any of the slides. They just have a very fancy camera at the back of the classroom and try to capture the movement. I saw a video of it, it's pretty nice. Try to capture the movement of the professors, and then like I think that's gonna move automatically while the professor is like walking around in the front and trying to record all of the video, all of the writings on the board. Okay, so far I feel like I'm okay, comfortable now, but I think things can I mean, the technology thing can go around in all different kinds of ways. So I don't know now, but so far that's what I want to do. Do you have a? Oh, okay, yeah. Because if you do, I have to do that to you. Okay, right. So this is part of the pilot study. So I just want everybody to know about this because the thing is, like, we joined this kind of pilot project because we are hoping to explore like different ways to enrich the offering. But still, I mean, if you really don't like the format, if you think it's really bad, you're not forced to, like, I won't force you to take this, of course, and you still have the freedom. But I just want to know, like, to give an early heads up that this is going to be how things going to work for the entire semester. Okay. Yeah, but the thing is, I mean, we all want feedback, and then if you have any suggestions, if you don't feel like it's like you can learn as much as you can do in the traditional face-to-face course, let me know, and let's see if there is anything can be done. That's actually part of the effort that we're trying to make in order to see if this can work. Okay, and okay, so currently there are 18 Vassar students. I think someone dropped already, so probably 17. And so far, right now, I think it's 7 remote. No, not because of the online component. I think it's more about schedule. And there are 7 remote students so far. I don't think everybody's Skype Zoom in today. And I guess Grant, Julia, and Tuan. So I think if I remember it correctly, Julia is from Washington Lee. Yes. And Tuan, I think it's from Swarthmore, and Grant is from Haverford, right?
Yeah.
Okay, cool. Yeah, so I think we got, oh yeah, thank you. yeah, you can show your face. Anyway, so we can see your nodding, but thank you, okay, so what was I saying? Okay, so we got 7 students, I think 4 from, let's see, 4 from Swarthmore, 2 from Haverford, and 1 from Washington Lee. Okay, so that's what we have right now. I think this is going to be the most that we have. I don't think at this moment anybody else going to join, but we're trying to, yeah, like in any way, if we can all get to know each other magically through some online thing, that would be great. And I think I would try to incorporate that in part of the pedagogy as well, to see if we can team up students from here together with people from there to do some tasks together, etc. So yeah, it's a very steep learning curve for me as well. So anyway, so we have probably 17 plus 7, so that's like 24 students, a large class for 300 level. But so that's why, if you notice earlier in the syllabus, I wrote that the project gonna be done individually. I just changed my mind. You can do it individually or you can do it in pair. Otherwise, yeah, it's just gonna be too much, I think, for so many people doing individual project. Plus, I mean, team learning itself or teamwork itself is highly encouraged anyway. So yeah, so that's one change. I will talk about that later as well. So for the format, lecture is going to be synchronized online, just like now, and it's being recorded for remote students. And earlier, Eli asked the question whether we all have the access to the slide, to the recording as well. So everybody's going to have the access to a recording. So I guess I have one more thing. For the attendance of Vassar students, up to you. I'm not taking any attendance, but you still encourage, like, because the thing is, if you have to miss a class or for some reason, you can still watch the videos later, okay? But I still think it will be definitely like worthwhile trying to come to the class, as well as for the remote students. I think it will be nice if you can Zoom in real time, because we can have better interactions over there, okay? And one thing that we're gonna do that I know, because there are 6 students from the Philadelphia area, so actually mid-September, I'm actually going to go down to visit, because people like been doing this recommend that you should meet the remote students as soon as you can. So as long as they can see you once, they know you better and they feel much better. I don't know, but that's what I'm going to do. And so for that matter, for that Wednesday's lecture, I'm going to I think I'm going to do it over there. And then that will be not on Wednesday. It's sometime on Thursday or Friday, but I'm going to record things. I will still like coordinate with here. If you want to all Zoom in together or just like one by one, that's fine as well. But just a heads up, that's something we're going to try for just once, okay? But every other lecture going to happen at Vassar. Thank you, Katie. Yeah. Okay? Okay. All right. That's okay. Oh, I feel that I prepared too much. Sorry. Okay. just a little bit more about this online teaching and learning thing before I start to share what I have experienced before. Anybody has any like online teaching or learning experience that you want to share? Okay, give me a second. Okay, so Eli has. Okay, so we have Eli here. Okay, and Eli, it's over there, like the video. So, but anyway, okay. So you can, I think this.
Okay. In high school, I had a chemistry class that was a flipped classroom where we did problem sets in class, and we had recorded lectures that we listened to at night. I really liked it because I could like fast forward through the parts that were making more sense to me, and then slow down for the parts that were more difficult. So I think having the lectures online is really helpful.
But those are mostly like shorter videos of different topics, and then.
No, they were like full lectures. They're just
full
recorded
lectures.
lectures. Yeah.
Okay.
And I mean, obviously, we'll be in class for this time, but to be able to go back and rewatch some of the parts that were harder is helpful.
Cool. Thank you. Anybody else? No? No one? Never took anything online? Okay. Okay, so for me, that way. Okay, so actually back in grad school, I think it's 2014. So when Coursera was very popular, so I went to Duke for my PhD degree, and Duke actually, and among many other schools, has been very active in providing online courses for everyone online. And so back then I did a TA, teaching assistant job, as a community TA for Coursera course, and that's just like our Math 141 here, Introduction to Statistics. So that, I don't remember how many students are there, but I think it's definitely in thousands, and it's all over the place and different time zones, et cetera, et cetera. So I worked as a community TA, meaning that I don't think I was grading, but I was, so this is something we're gonna try to do as well, is on Moodle, I'm gonna start doing more like discussion boards. And then people can post questions and answer and have some interactions over there. So back then, I think, as a community TA, every week I sign up, like I sign in for 2 hours to answer those questions. And it's new, like crazy number of them out there, because so many people sign up for the course, and there's a lot of questions about the course itself, about the material, about the logistics, et cetera, et cetera. So it was, I would say, an interesting experience, but it was really hard, I think, to make it very efficient, okay? But I just want to say, like, because this is also, that is also like online teaching and learning, but this is different in the sense that we are much smaller in scale, as well as, I think, yeah, we have Bayan as the stats intern and grader and TA for this course, as well as I will be, I wouldn't say monitor, but I would check like all of the things very regularly to make sure that you all feel that you have equal access to the material, not only for the Vassar students, but also remote students as well. Okay, but there's so many different things. Like I said, I think might go wrong in terms of technology and the experience. So make sure that keep me posted with any things that you have in mind. And I think that will be a very important lesson that we're trying to learn here as well, okay? And I kind of want to skip the second part, but let me just share a little bit. So some of you might know that I've been taking Japanese class on this campus for 2 years. And now I'm in a stage where I feel like going to because so I'm native Chinese speaker, and then learning Japanese through English is really hard, because I have to translate, like doing so many different things in my mind. And also like because of the schedule, I won't be able to go to the third year class anymore. So now I actually sign up for I just started in August 1st, and I started like an online Japanese class taught by a Chinese teacher back in China. So we have this time difference, et cetera, et cetera. But everything is online. And so far I really liked it. And I realized, I think, so it's different from what we're doing here, of course, but I do feel like big potential for online and hybrid teaching and learning. I think they have been doing that for so many years, and there are so many resources and like practices out there. So, I mean, yeah, it's hard for me, like we won't be able to promise that it's gonna be exactly the same as face-to-face, but I think for us, but I think we're trying to utilize the fact that we actually have all of this online thing that we can do, and how to make it work for everyone involved in the class. Okay, all right, okay, so one lesson so far that I learned from some of the reading is we really should try to view community and collaboration, and we will talk more along the semester, but so far I think things like online discussion board, et cetera, will be something we're definitely going to be doing. Okay, and please give feedback and share your thoughts anytime. Okay. Okay, so really quick over here, and then we're going to start talking about the Bayesian part. So the course objectives, earlier I broke the material into 3 parts: the inference, computation, and applications. And I show all of the topics and as well as the textbook chapters associated with each part. But I also think that there's one extra part hidden over here is review of material from prerequisite courses like calculus, linear algebra, and probability. Pretty much is the 3 prereq courses that we have. So I think for all of this, each part, you will see that it's going to be a combination of, say, readings, lectures, labs, homeworks, discussions in class and online, and ultimately a project. And some activities and multimedia, when I put down multimedia over here, it's more about, say, like if I want to provide some review material through videos, that will be the multimedia thing that I'm talking about. So I think be prepared that we're trying to achieve the regular course objectives as we have as a face-to-face course in a more varied form right now because of the nature of the class. So there will be some experiment. I want to move certain material online, and then that will be a little bit like a flipped classroom style, that maybe I will ask you to watch like a 5 minutes video beforehand, before you come to this particular lecture. So we're gonna review some of this instead of spending the time in class. So one thing is I think that can save a little bit of time, but also for certain things, for example, I was talking about this review of linear algebra, I think it will be easier done if it's recorded for 5 minutes, and then you can go at your own pace if you have certain things I don't understand. Okay, so for example, that I think that will be some of the experiments that we're gonna be doing. And then the course project is like the capstone experience in the end, and we will talk more about that later. But so far, I think a lot of people, I think, will prefer doing an application of a Bayesian analysis to a data set or to a problem that they want to solve. So in that case, I think that will be things like certain applications, say if you're econ major as well, if you want to do some time series, then if there's going to be like a critical mass of people who want to do that, then we're going to spend like a lecture maybe towards the end, because we cannot do that early because they require all of the material from before. But if we can afford one lecture on talking about the basics to build up the building blocks, then that would be nice. And then that will be one way you can do the application, okay, for your project in particular. So just for like as an example. Okay, grading, it's all in the syllabus, and homework is 35%. The participation here, 5% is mostly gonna be like discussion boards, et cetera, et cetera. So I will give more information over there. I just want to leave 5% there to encourage people's participation. Midterms, we only have 2 midterms for this class, no final. Each midterm is 20%, and the project is 20%. So for the 20% project, I said that you can do it individually, and then your score gonna just be the final score. If it's gonna be doing pair, if you want to do it with another student, they're gonna be like about like a 10% like peer evaluation over there, just to make sure that everybody's contributing equally. Okay, so there will be more information, more detail about that later. Okay. Okay. Any questions? Concerns? Excited? Not excited? Worried? Okay. All right. Okay. Yeah. So we can keep talking about all of this. Send me emails. I will start a discussion board, like a thread of conversation over there as well. But now let's get started about some introduction of Bayes rules, Bayes theorems, and then how to interpret probability. In particular, seeing the difference between the interpretation of probability comparing to the usual one that we have seen. And we call them the classical inference. So if you have taken 141, or I guess econ, is there like econ 210? Okay, so that's more about the statistics part, right? Like some, no? Econometrics? Okay, so pretty much, I think most of the stuff that you have heard or you have learned before, like hypothesis testing, p-values, you have taken any of those. it's from the frequentist, it's from the classical inference point of view. So Bayes' theorem and Bayes' rule itself is just a totally different way of interpreting the probability as well as all of the inference, computation, and applications. So I want to give you an overview at the beginning. The thing is, because not everybody has taken like a mathematical statistics or even intro stat, because I know like here, because of the core curriculum, some of you probably just started with 241 probability, and then you just come here, right? So for those of you, you probably don't know much about like p-values, etc. anyway, because you have never seen that before. So the goal, I think, for this course is we won't compare. Like I'm going to compare a little bit at the beginning between the two schools. I mean, the frequentist, classical, comparing to the Bayesian way. But that's the most we're going to do. Okay. So this class, we're going to think throughout the semester, we're going to think like a Bayesian person and then just interpret the probability doing everything in that way, because otherwise it's going to be hard for me to assume, you know, all of the other stuff before. Okay. But the thing is, based on my experience from last year, I think there were 11 students. I think at least 2, 3, 4 maybe students never took, like only took 241 and just come here, know nothing about all of the other frequentist stats out there. And it's just fine, because it's, you can think of doing this class as just starting from, as long as you know probability, you know calculus, and then you know linear algebra, you can start from scratch to learn about Bayesian. It just pretty much stand alone. And you don't need to know about all of the other stuff, okay? But of course, the other stuff are useful, and that's actually most people are doing or using out there, like in industry, like in companies when they're trying to do analysis. Most people still use frequentist or classical inference because it's fast and it's easier to do. But I think it's definitely important that in the future, even if you just take this, you don't know much about the other way, I think it will still be useful to know, because that's most what people have been talking about. But Bayesian methods and Bayesian statistics is gaining, I think, momentum since 25 years ago, because the computation has been improved a lot. So a lot more people are doing this, and then a lot of research is being done, say like comparing these two methods or comparing different models. So it'd be nice to know both, okay? So I just want to say, maybe my guess is maybe like 70% of us actually know some other set methods, but the 30% don't. In the future, so for this class, we're only going to talk about Bayesian methods mostly. But for whichever category you belong to, I think it will be nice in the future, no matter what, you know both. And then, but again, it's not the goal of this course, but it's good to keep in mind that you still have all of the other things you can do. Okay, so I was just saying, say significant tests like hypothesis testing, all of the confidence intervals that we dealt with before, p-values, etc. They're all forms of classical. So okay, I'm gonna use classical frequentist interchangeably for this class. We're just gonna refer to the frequentist methods or classical methods, and then significant tests, confidence interval, p-values are just examples of that, and those might be the things that you've seen before. And I just want to pose a question here. So when might classical inference be inadequate? So because if you took like 341, like mathematical statistics, or 141, say introduction to statistics, we just gonna, you have all the numbers, I'm gonna plug in, and this is the p-values I get, and I'm gonna try to produce a p-value and then interpret it. That's pretty much what people like a standard course will do, which is not bad. I think for introducing like the entire area, I think it's good, and it's very concise and good. And but we never really talked about, I think, what will be cases where such a classical inference cannot work that well. So my example here is, suppose you flip a coin, you don't know if it's a fair coin or not. So if it's a fair coin, it's going to be 50% heads, 50% of tails. But suppose we don't know, and we want to make inference about it. We want to know what is the probability of getting tails, for example, okay? So suppose you don't know about that, and that's what we want to know, and we flip a coin, and we do it 3 times, and we got all of them tails. Okay, only 3 times, and all of them tails. So if you have done any kind of frequentist or classical statistics before, you'll notice that you have a sample size of 3, and all of them. Okay, so let's see. If we define, okay, let's do, because we don't know probability of heads, we want to know like the probability of heads. So let's define that as the success, because it's a binomial, right? Like Bernoulli trial here. And let's define the heads to be success, tails to be failure, and you get sample size of 3. and you get, let's see, 3 times. So you get 3 failures out of 3, right? Okay, so the sample percentage of the success for this case, because you get 0 success out of 3 trials, so the sample percentage is going to be 0, right? Yeah, and that's all you have as the sample, like as the data. But how can you make use of this 0% sample percentage to make inference about the probability that you want to know? Because I want to know what is the probability I can get pet, but I get 0 out of 3. Okay, do you think 0 will be a good estimate here? I guess a lot of times people want to do a little bit more, right? You want to do a little bit more trials to see if you can do that. But this is a very simplified situation. But the thing is, a lot of times, I think in real applications and in real data collection, you will notice that you have a really small sample size. And then if you still remember all of the like central limit theorem, law of large numbers that you might have heard before, then all of those, so all of the, say, for this case, I think it's inferencing for proportion, right? We're trying to make inference for proportion. So you have a set of formulas that you can do, like I'm gonna have a p hat and then plus or minus 1.96, etc. All of those like p-value calculations and confidence intervals, etc., they're all built up based on the assumption that there are large number of, like the sample size is large and you are doing this experiments repeatedly, okay? But so for example, here we only have 3 and it's 0 success. So first of all, like p hat is 0. No matter what you do, I mean, because the confidence interval you can compute is going to be negative something to positive something, for example. And then it's just not going to work if you want to use it in the traditional way. So again, this is a very simplified situation, but I want to show you that even for this toy example, that if you try to go with what we learned before, if you try to, so for a lot of people, for 141 students, they probably just going to plug in the formula and do it. For 341 students, I guess we never got that far. But if we did that, we probably would try to want to like derive why that is the case, why that is, say, can we use the norm approximation over here, etc. But the thing is, even in theory, that's beautiful. All of the situations, say like situations like this, it wouldn't work because it's just too small sample size and sample percentage has a 0. So what are we gonna do? So let me introduce you the Bayesian methods here a little bit. So Bayesian way of thinking about the probability is each person gonna have its own probability. It sounds a little bit like sketchy at the moment, but yeah, stay with me at the moment. So say, for example, if I don't know about this coin at all, somebody just gave me this coin, and what would you guess? Like the percentage of getting a hat, like the success probability. You don't know anything about the coin. If you're gonna have a guess, say each of you gonna just guess what the probability gonna be, what you're gonna guess. 50%? Anybody else? So I can do a 70. It's okay, right? Because we don't know what it is. So the point here is each of you can just have your own probability of success here, and we actually call it prior probability. Later we're going to move it to distribution. So later we're going to do more about that. But for now, let's just think about a prior probability of success. So Katie has 50. Everybody else? 50? Okay. So, okay, so I can have 50 as well. So suppose we all think it's 50. And now the thing is, if we start the belief that it's going to be 50, and now I'm going to flip it once, I got 0, like I got a tail, right? So that means naturally, like intuitively, you think that probably going to go down, right? Because now I get some evidence. I believe it's 50. I thought it's fair. And now I got evidence saying that, oh, it's a tail. So maybe naturally, I think people will start to reduce. Right? And then second time, I got another tail. So that's another data point. And now I'm probably going to reduce that more. And I get 3 and get 4. I mean, there's so many things going on here. Some people might argue that, oh, because of like law of large numbers, central limit theorem, oh, I have to do 100 times, and then I would know. So yeah, things are going to change. So say now I only give you 3 coins, no, not 3 coins, 3 flips, and all of them are tails. I got 3 failures. In theory, I think intuitively, the probability of success that I'm going to have is going to keep reducing, right? So this is the general idea of Bayesian stats. Pretty much, I have, or everybody has a belief, and you can start with whichever you have. Katie has 50, I have 70, like Lam, I have 90, etc., etc. maybe the coin looks very weird. I'm gonna guess something different. Yeah. But anyway, so each of you can have different prior beliefs, but we are gonna keep updating because the goal is to know about what is the probability of success, right? I start with 50% and then I start flipping it. I got a failure, I'm gonna reduce my inference about the success. I got another failure, I got more failure, or maybe later I'm gonna get a success and I'm gonna keep going back, right? So the process of, I start with the prior belief, we call it prior because it's before seeing the data. We start with the prior, you look at the data, you collect more data, and you keep changing your inference for the thing that you want to know. For this case, it's the probability of success. You keep changing it as you update, as you get more data. Okay, so that's the process of Bayesian analysis. I mean, for this simple toy example, it's pretty much, I start with the prior probability, I collect data, and then update it. And once I update, it's gonna become posterior. So that's after you see the data. So this will be the terms that we're gonna see very often. For here, just about probabilities, because we just have beliefs about certain things. For example, here, the coin. And later, because we can do more complicated stuff later, we're gonna move from probability to distributions. You can put different distributions on the thing that you want to know, because you also want to know. So for example, I want to know this probability of success, right? If I just say 50, oh, just a point estimate, right? It's just 1 point, and I'm just gonna keep changing it. And then the thing is, so you can keep updating, maybe later it becomes 40% because you see more and more failures. But to be more, I think to be more accurate in some way, that, I mean, this probability, the probability of success, I say is 50, but at the same time, I can also assign some uncertainty about it, right? So instead of just 1 point, I put 50%, I'm gonna put, say, a uniform distribution to accommodate for because if you want to make inference about something, we not only want to know the point estimate, but also the uncertainty, right? That's the mean and variance that we have talked before, like in different courses you have taken before. So here, we're gonna do more of that later in a more rigorous way, but here I just want to mention that instead of like 50%, I might want to put a uniform distribution, saying, oh, it's equally likely to be anything between 0 and 1, to incorporate the uncertainty about this probability, okay? And then so later for the actual, I think later when we talk about the actual Bayesian inference, it's gonna be more about, okay, I want to make inference about something, I'm gonna put a distribution, and I'm gonna combine that with the data. And then I'm gonna update my prior to be the posterior, and the posterior really gonna be a distribution as well, okay? And so for that, from that distribution, I can summarize like the mean, the variance, et cetera, so I'll be able to know more about the quantity I'm interested in. So this is the general idea. Okay? Any question? Okay. All right. Okay. Okay, yeah, Bayesian inference provides a formal method for quantifying and incorporating our prior beliefs into inference. Okay, so earlier we were talking about each person can have a belief, right? But then there may be good beliefs, there may be bad beliefs. Some are better than the other. And so later we're gonna also explore like this idea of choosing different prior, because the prior that you choose might change the results that you have. But in general, some people like to, so for example, we're gonna get to this later as well, but just to give you some example at the beginning, some people might put very diffuse prior. We use the word diffuse, just not showing too much personal belief. So for example, for the probability of success, I put a uniform. So it can go anywhere between 0 and 1. So that's very uninformative. That's very not strong personal belief. I think it can be anything. And it's like equally likely, right? For a uniform distribution, okay? So that can be like very uninformative, diffuse prior. So in that case, you will see that, we're gonna see the exercise later, that if you have a very diffuse prior, then a lot of the inference that you're gonna be driven mostly by the data. Because say I start with 0 to 1, and now I get 10 successes and 0 failures. If you wait, later we're gonna do like both analytically, I think, as well as like through the R simulation. You will notice that for the posterior probability or posterior distribution for the success, gonna be driven very high, right? Because I'm getting 10 successes out of 10 trials. Okay, so that will be, some people would like to do it for the diffuse prior. But so that's the thing. So for example, people like to discuss what kind of prior we want to give, right? Because sometimes like good prior gonna help the bad prior gonna hurt. So sometimes if you don't know, actually a lot of times if you don't know, you're just gonna put a diffuse prior. We're gonna learn about different types of diffuse prior for different types of data. And then you're gonna let the data drive the inference. But sometimes you might have very strong prior, and the strong prior that you have very strong evidence that this is true. I'm gonna show you an example later, okay? And then that will be the case, I'm gonna be very strong, I'm gonna choose a very strong prior, and then that will be the case where the prior information gonna matter a lot in your inference, because, I mean, the data that you get might not change that much. So the thing is, for the posterior, it's a combination of the data and the prior, okay? But the good thing about the Bayesian statistics, I think, is you keep updating if you get more data. So you're getting the truth in some sense, right? Because I don't know anything about this, or if I have a strong belief, I say it's 50%. But if I start to get like 100 heads or like 1,000 heads, the data is telling me that, oh, I should drive up my success probability, right? So the data are gonna drive that up. And then, so in this sense, we're thinking, as a Bayesian way of thinking about it, we're gonna let the data help update our belief. But we still start with the belief as the prior probability. Okay? All right, yeah. Maybe a little bit overwhelming at the beginning, but I just want to speak out like all of these ideas over here, so you have some food of thought. So why Bayesian statistics? I talked about with the toy example, and so this is named after the 18th century minister and mathematician Thomas Bayes. So that's his last name, and then it's Bayes theorem, and then we call like whoever works or whoever believes in the Bayes statistic will be called Bayesian. That's just how the words worked out. And so I put down three aspects over here. For example, earlier what we're talking about, if you have some strong belief or some strong evidence of what you want to incorporate in your analysis, then the modeling part has the good feature of incorporate the prior belief or domain expert knowledge. And theoretical, which we actually won't do too much in this course, but just don't worry about that much. And but the theoretical part for the Bayesian methods, it doesn't need a large sample assumption. Things will work even if it's small sample size. And then computation, I talked about a Markov chain Monte Carlo, MCMC. So the Bayesian methods itself really took off, I think about 25 years ago, around, I think 1990, when the invention of GIF sampler took place. And that just, because earlier a lot of things were just done by hand, and then all these beautiful results, like all of this stuff, but computationally is just not doable. But then starting around 1990, some of the more, so pretty much MCMC was invented, and then things took off drastically after that. And actually when we get to, so GIF sampler is a separate topic that we're gonna talk about when we get there. And we're actually gonna read a research paper about it as a whole class, and then discuss about it as well as part of the class. All right, so just another person you might have heard before, Nate Silver. So he's pretty much like a celebrity statistician now. He used Bayesian approaches. So this is what I have when I taught last year. I just put this down, predict the result of 2008 and then also 2012. So for 2008, he was using Bayesian methods. It's very complicated, of course, but overall, he's still like using the approach, and he successfully got 49 out of 50 states correct, plus DC. So DC is also correct in terms of like who won which state for the 2008 presidential election. He only missed Indiana. And for 2012, he actually got 50 out of 50, okay? And plus DC, okay? And then when I was preparing for this, obviously we had last year's election. It was just very hard for everybody to do any prediction. Anyway, so I tried to find what he had done. So, because for those predictions, they're doing like across several months, right? So what we hear, I guess, is the final prediction on the day of the election. So what I found is on November the 8th, 2016, 10:41 a.m. I don't know why people care so much about the exact time. But anyway, so he had Hillary Clinton with 71% chance to win. But if you compare it to the other major forecasters, and I guess if you guys were following the election that night, like even, I think I was looking at New York Times, like they designed this very fancy things of like the, what is it called? You know, it's maybe, what is that? like the pointer, like from 0 to 100%, and trying to show like the percentage winning of prediction. And I think like before I went to bed, it was like 95-ish% for, I don't even remember. Never mind. Sorry. So yeah, sorry about that. I should do my or I should refresh my memory before what I was talking about. But overall, I think it was a really hard prediction for any kind of forecasters. And comparing to the other major ones, I think he still did a relatively good job in terms of predicting the percentage of the chance of winning. Because the other ones are pretty much having between 85% and 99%, while he was doing 71%. But in the end, I mean, the thing is, this kind of chance thing is, you never know, because the final is wrong, right? It's just 0 pretty much. But still, I think based on the evidence, and he's still very active. He has a blog called 538. He started as a predictor for baseball games. I think that's how he got popular. And then he started doing this election. He does not only do, I think, presidential election, but also the other like state level, midterm elections as well. So yeah, if you're curious, you can follow his blogs. I think he does, he wrote a book as well. I think for those of you who participated Data Fest, one of the winning books is Noise and Signal. That's a book by him. Yeah. So yeah. Anyway, so he, I think we all very grateful for people like him because they promote pretty much the entire area. Say like statistics, of course, but also Bayesian statistics in particular, because of the successful stories and results, people get to know more about all of this. Okay. All right. Okay, so earlier we were talking about, so this is pretty much the only time that I think I'm going to compare this to, or put them side by side to see what is the difference between these two, and if there are any drawbacks in one or the other. Okay, so for the frequentist or classical, they define probability to be long round relative frequency of repeatable events. So that's how they're going to define it. Yeah, so probability of event A gonna be in the limit. If I can repeat the events infinite number of times, then it's gonna be the number of A happens over the number of times that the event happened. Okay, so in the long run, that's the relative frequencies. Okay, so I just wrote down like one-time events. Well, what if you just have one time and then you don't? Then it's hard to define the probability in this way. And also the small sample sizes earlier, like we saw, out of three trials, we got 3 failures. What we're gonna do? Okay, and for the Bayesian, I talked about it earlier as well. It's a subjective degree of belief. 2 people could have different probabilities of PA, and probability changes is new information. Here we call it new information generically, but it's really the data that we collect. Okay, just like what we were talking about. I flip a coin, I get a hat. I flip a coin, I get a hat. Those are the data that we get, and these are new information. And we try to incorporate those new information to help us make inference about the truth, if there is any. Okay, so I put down the Bayes rule over here. We're gonna look at it more carefully later. So it's pretty much a bunch of conditional probability manipulation. Yeah, it's not that hard. If you put in context, it's actually very straightforward. But the thing is, so that's what I was trying to say. Like before, like in the past, like before 1990s, like a lot of results, not only this, of course, like variations and more like theory about this is really nice, but it's very hard to compute. And later around 1990, when the computing methods took off, and that's how the whole field took off. Okay, but the core is pretty much just this Bayes theorem. You can do all of the things you can. So later we're gonna see, probably not today, but when we see like a new discrete situation where you can actually count all of the situations and then probabilities, it's a very easy math problem over there, okay? And I think somewhere like in 341, we probably did a little bit of that as well. But most of the course, of course, is not just repeatedly looking at this Bayes theorem with different situations. It's more about later we're gonna move to distributions. We're gonna have a data model because I believe the data are gonna follow a certain distribution. I believe the prior are gonna follow a certain distribution. How I'm gonna come up, how am I gonna combine these two? It's about the inference, how I can make the inference. How can I code it up? If I cannot code it up, can I use some R packages like Winbox and JAX I told you about? Can that help? Yeah. And then also applications that just gonna be so many different specific areas of research people like to do. Say for cognitive science, I think there's certain modeling that they do more. than any other model. And then like for hierarchical modeling, for example, at least I know that. And then time series, say like for the econ or for finance people, the particular methods or particular things that they like to do will be different. So those will be the things that we try to focus in this course. But again, all of the three parts I talk about, they're not like totally separate from each other, and they're going to intertwine here and there. So it's going to be back and forth, like reviewing things and then learning new stuff. Okay. All right. I guess I still have one more slide about this frequentist method. So let me see. Yeah, let me actually go to example 2. If you feel like it, read example 1. I think it's because not everybody knows too much about the frequentist method over there. But I think for example 2, a 95% confidence interval for an unknown parameter theta. How are you going to interpret it? For people who have taken, I don't know, intro stat or 341 or econ, I don't know, probably not 209, but 210. If you're given a 95% confidence interval, I don't know, say, okay, unknown parameter. Let's say the unknown parameter is the success of, probability of success. And let's say you got it between 0.61 to 0.75. What are you gonna do? Oh, let me try something over here. Because I can write here. Oh, no, here. What did I say? I said this to this, right? Okay. Yes?
Typically, I would think about this as 95% chance that the true parameter value lies somewhere in that.
Can you repeat that again? Yeah.
95% probability that the true parameter value lies somewhere in that observed interval.
Anybody else?
It's the 95% chance that that interval contains the true value, which is just like slightly different, but it's showing that the interval is what has a distribution versus the actual true value.
Okay, we have 2 opinions. Anybody else?
I think strictly speaking, it was 95% of the time that value will be in this interval.
95% of the time, that the parameter is going to be in this interval. It's confusing, I mean, in a way, right? I mean, the fact that with, like some of you have taken like 341 even, and like even, yeah, I mean, just, the thing is, okay, so what do you think is the right answer? It's okay if you get it wrong, because the point I'm trying to make here is I think a lot of the frequentist approach itself, say just interpreting a confidence interval or a p-value itself is not intuitive. So what Eli said at the beginning, I think will be the most, so if I give you your interval and I say that I have 95% confidence, intuitively people would think that, oh, there will be a 95% chance that the parameter, unknown parameter theta are going to fall into this interval. Right? Intuitively, I think people would like to do that, and I think it makes sense as well. But the thing is, the frequentist approach is not that. It's exactly what Tony and Nick, yeah, what Nick and Tony talked about. You guys are talking about the same thing, yeah. And it's just 2 different ways of interpreting. But in the frequentist approach, we're just talking about, okay, if it's a 95% confidence interval, that's meaning that 90% of the chance that if I do, okay, so if I do so many different confidence intervals, and 95% of them going to cover the truth. Okay, okay, that's what at least the theory behind of the regular like confidence interval from the frequentist approach. Okay, however, I think most people will feel that that's more intuitive if we want to go in the first way, right? And then the first way is actually how Bayesian is interpreting the confidence interval. We actually call it credible interval. Later we're going to get to that. But I just want to use this example of saying that. So I have the 2 points over here. So is this an interval that has probability of 0.95 of containing theta? So for the frequentist and classical, it's actually no. just like what we talked about earlier. Okay, it's 95% of the chance, like 95% of the time that if you do it so many times, you're gonna cover the truth. It's not directly related to the probability of having it contained. Okay, but if you think about the Bayesian approach, we're gonna talk more about this later as well. It's actually, if we're gonna talk about 95 credible, so it's actually called 95% credible interval in the Bayesian paradigm. It's gonna be directly related to the probability of the hypothesis or like the probability of containing it. So if you're getting a 95% credible interval in the Bayesian methods, the confidence interval or the credible interval 0.61 to 0.75 gonna be the interval that we have 95% chance I'm gonna cover it. Okay, so I just want to use this as an example. I'm not saying that one is better than the other, but it's just so many different things going on. Like say nowadays people don't like, philosophically people don't talk too much about the difference or like debate because they're like merits in both and like there are differences here and there. And I think for a lot of people, like for practical users, oh, I would go whichever is useful, whichever does well, and I'm just gonna go for it. So we won't have too much debate about whether one is better than the other or we should choose this one over the other. But for this example, so I'm gonna finish after this slide. For this example, I think there are just two issues here because first of all, they think frequentist classical and the Bayesian, they think about probability differently. So one issue here is philosophically, like what is the best way of quantifying uncertainty? And the second one is more about, I think it's the point that I want to make more with asking 3 different students offering their answers so you can see that there are some debates, people understand things differently, and in particular, how statistical users, so I call it, or people call it pragmatic problem issue here, is how the layman is actually gonna interpret statistical conclusions. I mean, I definitely had a really hard time, I think, teaching in 141, trying to practice and convince again and again of how to interpret a p-value and how to interpret a confidence interval. The thing is, and I think that actually demonstrates that how unintuitive it is and how easy it is to get wrong. And if you read articles about like people trying to use statistical statements about p-value or confidence interval, it's all over the place. You never know, right? So I'm not saying that it's bad, but it's just like even at the very introductory level, I think the frequentist method has the difficulty of educating people or educating people's statistical literacy in that sense. And I think that will be just like one last example here, actually, I think, about why we should start thinking about like thinking problem as a Bayesian person, as a way to quantify the probability of an event and then use the prior combined with the data to come to the posterior. Okay. All right, I definitely gonna start here and okay, thank you everybody. I think this is, yeah, I thank you all as well. Over here, yeah, and yes, so later today I will post this and send you the link and I think we're gonna go from there. So, go ahead. Yeah, so for everyone, yeah, anything that you have concerns about, like about the format. I mean, we didn't go as far as we can for the material because I was trying to explain the model itself, but yeah, we're gonna definitely like, I mean, the focus is still Bayesian. It's not about like the online model, but it's just part of it and we're just trying to experiment it. So let's keep talking and then, yeah, so see you on Wednesday and I might, if I get some time like tomorrow or today, try to make some videos of stuff. Yeah, just watch them, give feedback, and then it's gonna be related to the course, of course. Okay, all right, thank you so much. Let me